So we have been looking at different units in the architecture of ARM Cortex-M3. We have seen the registers, operation modes, uh, uh, different bus interfaces, right, and the memory map, memory protection unit, and all. Today we will see yet another thing in the architecture, that is interrupt controller. We have something called nested vectored interrupt controller, that is NVIC, within the processor core of ARM Cortex-M3. So yeah, the ARM Cortex-M3 processor includes an interrupt controller called NVIC, that is Nested Vectored Interrupt Controller. It is closely coupled to the processor core. It is within the processor core, and it provides a different features. Provides a number of features like nested interrupt support, vectored interrupt support, then dynamic priority changes support, reduction of interrupt latency, and interrupt masking. So what are these things? What is nested interrupt support? Nested interrupt means interrupt within an interrupt. Suppose an interrupt is being served, and when the interrupt service routine is being done, if at all another interrupt occurs which is of a higher priority than the presently servicing interrupt, in that case, the presently served interrupt, that service routine, interrupt service routine will be kept on hold, and the newly arrived interrupt that will be served. That means when an interrupt is being serviced, another interrupt is accepted, and that is served. That is called nested interrupt support. So all the external interrupts and most of the system exceptions, they can be programmed to different priority levels. So each of the exceptions or interrupts, they can have different priority levels. When an interrupt occurs, the NVIC or the interrupt controller, it compares the priority of the newly arrived interrupt to the priority of the currently running interrupt. If the priority of the new interrupt is higher than the current level, then the interrupt handler of the new interrupt will override the current running task, right? The current running task will be that will be interrupted. That will be it will be preempted, and the newly arrived interrupt, that will be service first. So that's called interrupt within an interrupt, or it is like a nested interrupt support. If the newly arrived interrupt has a higher priority, then the currently running interrupt will be kept on hold, and the newly arrived interrupt will be serviced first. So then vectored interrupt support. What do you mean by vectored interrupt? Means the each interrupt, they are all predefined, and the starting address of each interrupt service routine will be located in a table that is called a vector table. Whenever an interrupt is accepted, the starting address of the interrupt service routine, that is called ISR, is located from a vector table in the memory. The starting address of interrupt service routine will be there in this vector table. So interrupt service routines will all be stored somewhere in the memory. So they will begin at some particular addresses. So the address of that interrupt service routine will be there in a table, right? So there is no need to use software to determine and branch to the starting address of the ISR, because the starting addresses are already there in the vector table. So it takes less time to process the interrupt request. So that is called vectored interrupt support. That's why it is called nested vectored interrupt controller. Then another feature of this is your dynamic priority changes support. So there can be priority levels, they can be changed dynamically. We say they have priority levels, but that can be changed during the execution of the program. That's called dynamic priority changes support. Priority levels of interrupts can be changed by software during runtime. So interrupts that are being serviced are blocked from further activation until the ISR is completed. So their priority can be changed without risk of accidental re-entry, right? So whenever interrupts are being serviced, they are blocked until that particular ISR is completed. That particular type of interrupt cannot occur again. So even if a priority of that particular thing changes, the in between it cannot happen. There cannot be an accidental re-entry even if the priority changes. So dynamic priority means during runtime the priority can be changed. Then reduction of interrupt latency. Interrupt latency means time required to serve an interrupt or to complete that particular interrupt. So there is, within a less time the interrupts can be served. That's why you say there is very less interrupt latency. The Cortex-M3 processor also includes a number of advanced features to lower the interrupt latency, like automatic saving and restoring some register contents, reducing delay in switching from one ISR to other, handling of late arrival in interrupts. So all these features are there. That's why it offers reduction of interrupt latency. Then another thing is interrupt masking. Masking means you can disable certain interrupts by using some interrupt masking registers. We have seen this. There are some registers, special registers for masking the interrupts. Interrupts and system exceptions can be masked based on their priority level, or they can be masked completely using interrupt masking registers like base pry, pry mask, and fault mask. So why we do this is to enable to ensure that the time critical tasks, they are not interrupted and they finish within the particular time, right? If they keep getting interrupted, it will take more time to complete the time critical tasks. So interrupts are disabled or masked in such cases. So they can be used to ensure that the time critical task can be finished on time without being interrupted. So these are some features of your nested vectored interrupt controller. So next we have interrupts and exceptions. So this interrupt controller, it deals with the interrupts and exceptions. So what are these interrupts and exceptions? So whenever the processor needs attention, it will some signals will be sent by some particular processors or maybe some hardware to the processor to indicate the processor that it has to stop its current execution, and there is some critical thing that has to be serviced first. The Cortex M3 processor implements a new exception model that is introduced in the ARM version 7 architecture, which enables very efficient exception handling. So it supports a number of exceptions, including a fixed number of system exceptions and a number of external interrupt requests. Fixed number of system exceptions means they are within the system, and external interrupt requests can be given through external interrupt request pins connected to the microprocessor or controller. That is called interrupt requests, or IRQ, external interrupts. Then the interrupt priority handling and nested interrupt support, they are all now included in the interrupt architecture through NVIC. Right? Interrupt features are implemented in the NVIC, which we have seen previously, nested vector interrupt controller. Apart from this external supporting external interrupts, Cortex M3 also supports a number of internal exception sources, that is system exceptions like system fault handling. So there are a number of predefined exception types which is given in this particular table, and each of the exception will have a particular number. Okay, so based on an exception number, it will determine what type of exception it is, and you can set a priority to that particular exception. So exception number, if it is 0, that means no exception has occurred or no exception is running. Okay, it's not applicable, exception type and priority, and that means no exception is running. Exception number 1 is reset, the system reset. When you reset, that is the exception number 1 that has got the highest priority. The highest priority is -3. Okay, highest priority is -3. That means it has got highest priority, that is system reset. Then NMI is non-maskable interrupt. It cannot be disabled. That is non-maskable interrupt. That priority is -2. Then hard fault, some hardware fault. All fault conditions, if the corresponding fault handler is not enabled, then all fault conditions will be treated as hard fault. That is exception number 3. Its priority is -1. -1 means next to -2. Okay, then whatever comes will be 0, 1, 2, 3, and so on. Okay, they can be programmable. They can be programmed, by the user. Exception number 4 is memory management fault in the memory management. If at all there is a violation by a particular process to access some part of memory which it is not authorized to access, then this memory management fault will occur. Then exception number 5 is bus fault. There is error in the bus, prefetch abort or data abort. Data is not properly fetched. In such cases, bus fault happens. Then exception number 6 is usage fault. There is error in the program that causes exception number 6. Then exception from 7 to 10, they are reserved. They are not used. They are reserved for some purpose. Exception number 11 is the supervisor call to the kernel. Then next 12 is the debug monitor. For debugging the program, like breakpoints, watch points, external debug request, right? For those, we have kept this exception number 12, that is debug monitor. Exception number 13 is again reserved. Number 14 is pend service, that is pendable request for system service. Number 15 is systic for the system tick timer, right? Then from 16 to 255, you have actually 240 external interrupts. So it supports maximum 240 external interrupts. Interrupt request number 0, interrupt request number 1, interrupt request number 2, until interrupt request number 239. 0 to 239, that is 240 external interrupts. So that is the maximum number of external interrupts it can support. Again, the maximum number, it is limited by the chip manufacturers. They can either give support up to 240, or they can limit to certain level less than 240. Right? So these are the different exception types. A number of interrupt inputs on the Cortex M3 microcontroller again depends on the individual design. The typical number of interrupt inputs is normally 16 or 32. So besides the interrupt inputs, there is also a non-maskable interrupt input signal, right? So that has got the highest priority among the interrupts after reset, right? In most cases, NMI could be connected to a watchdog timer or a voltage monitoring block that warns the processor when the voltage drops below a certain level, right? Whenever the voltage drops below a certain level, it has to be taken care first. NMI exception, it can be activated anytime, even right after the core exits reset. Just after reset, you can activate this NMI exception. So this is another table of a similar thing. They are given in two different cases in the textbook. You can either take note down this particular table or this one. They are one and the same, just some differences. Same, like exception where one is reset, then NMI, then hard fault in that priority level. Then other things, it is programmable or settable. I mean, the priority of other exceptions, they can be programmed by the user. Then there is vector tables. We said it provides vectored interrupt support, right? So, vectored interrupt support means there is a vector table which stores the starting address of each type of interrupt service routine. Okay, I mean, for each interrupt service routine. So when an exception event takes place and it is accepted by the core, the corresponding exception handler is executed. So which handler, I mean, exception type is already known. Based on what exception type the exception has occurred, the particular interrupt service routine has to be executed. So how do you find which interrupt service routine has to be executed? Where is its address? Its address is there in the vector table. To determine the starting address of the exception handler, a vector table mechanism is used. So what is that vector table? It is an array of word data inside the system memory, each representing the starting address of one exception type. Again, this vector table is relocatable, and the relocation is controlled by a relocation register, which is there in NVS. That means the table can be relocated in different memory addresses. So after reset, this relocation control register is reset to 0. That means it will start from 0 when you reset. Therefore, the vector table is located at address 0, 0 after reset. That means it will start from 0, 0. Right. So if the exception type is 0, then at 0 you will have the initial thing, starting value of MSP. That is the stack pointer. Right. What is the starting value of the MSP? Main stack pointer. So that will be there in 0, 0, 0, 0. Then the highest priority level exception is reset. Right? If system is reset, what should happen? That is stored in next address. Next address is 0004. Why? Because each address is 32-bit wide. Each address is 32-bit wide, so it will take 4 memory locations from 0, 1, 2, 3. So in that memory location, this particular address is stored. Next location, that is at 4, 5, 6, 7, 4 memory locations. So one word means 32-bit in this case. So the reset, if it is reset from where the system has to start, that will be stored in address 0004. Then NMI, if the exception is NMI, then its address will be stored next at 8. 8 plus 4 is 12, that is C. There the next one will be stored. So each one will be of 4 bits. Okay, each one will be of 4 bits. So for each type there will be 4 bits. Till 3FF, it will be stored. So this is the vector table. So there is a table or an array in which the starting address of the interrupt service routines will be stored, and each address will take 4 memory locations because they are 32-bit addresses, right? So for example, if the reset is exception type 1, right? Reset is exception type 1. Based on the exception type, you can find the address. Suppose the exception type is 1, it is 4. The exception type multiplied by 4 will give you the address, right? Suppose exception is 5. 5 into 4 is how much? 5 into 4 is 20. In decimal it is 20. 20 in case of hexadecimal it is 14H, right? 14. So 14 will give you the address, right? The vector address. Suppose it is reset, its exception type is 4. The address of the reset vector is 1 times 4, that is 1 into 4, which equals 00004. And the NMI vector is located in NMI is type 2, right? NMI is type 2. Its starting address is there in 2 into 4, that is 8, at address 8. Suppose interrupt type 0 happens, interrupt request type number 0 happens, then that its exception type is 16. So it is 16 into 4. 16 into 4 is actually 64 in decimal. In hexadecimal, it is 40H. So it will go at 40H. It will find the starting address of its interrupt service routine. It will be there in 40H, and then it will be executed. So whatever the exception type you have, that multiplied by 4 will give you the address offset, right? So the address 0000 is used to store the starting value for the MSP, that is main stack pointer. The LSB of each exception vector indicates whether the exception is to be executed in the thumb state. Okay, the LSB indicates whether it is in thumb state or ARM state. In case of Cortex M3, it supports only thumb instructions. So the LSB of all the exception vectors should be set to 1. Okay, for all the addresses, whatever we have in these particular locations, the LSB of each of them should be 1. Otherwise, it will again cause an exception. It will cause an error because it cannot operate in ARM state. Our Cortex M3 operates only in thumb 2 state, right? So LSB should be 1. So that's one thing we need to take. Then coming to the instruction set, we have told in the beginning itself that Cortex M3 supports thumb 2 instructions. Thumb 2 instruction set means it is a mixture of 32-bit instructions along with 16-bit instructions. So it allows 16-bit and 32-bit instructions to be used together for high code density and high efficiency. So it is flexible and powerful, yet it is very easy to use. In previous ARM processors, the CPU had 2 operation states, right? We have seen this 32-bit ARM state and 16-bit thumb state. In the ARM state, the instructions are all 32-bit and they can execute all the supported instructions with very high performance. Whereas in thumb state, the instructions were 16 bits. So, there is much higher code density. That means in a lesser memory, more number of instructions can be written. Yeah. See, in most of the applications, we have the mixture of both ARM and the thumb ports. So, even when we mix these ARM and the thumb codes, there is actually overhead because we have to switch the states between ARM and thumb states. That there is overhead in terms of both execution time and instruction space. And ARM and thumb codes, they have to be compiled together and run. So this increases the complexity of software development and it reduces the maximum efficiency of the CPU code. So with the introduction of this thumb 2 instruction set, it is now possible to handle all the processing requirements in one state, that is thumb 2. In this case, there is no need to switch between ARM state and thumb state. So Cortex M3 actually does not support ARM state, operating all in thumb 2 state. Even interrupts are now handled with the thumb state, that is in the thumb 2 state. Right? So earlier in the traditional processors like ARM7 and all, there had to be switching between ARM state and the thumb state. So suppose the main program is in thumb state, right? Some critical code would be written in the ARM state, then there had to be some switching from ARM state to thumb state. So it takes certain time, right? So we had to branch with the state change, we had to change to ARM state. So there is an overhead with respect to time, right? And again, while switching back from ARM state to thumb state, again, there is an overhead. We are returning from ARM state to thumb state, again to the main program. So there is an overhead, right? With the introduction of thumb 2, where both 16-bit and 32-bit instructions are written together and they're compiled together, this overhead with the state switching is avoided. Since there is no need to switch between states, ARM Cortex M3 has a number of advantages, like no state switching overhead. It saves both execution time and instruction space. There is no need to separate ARM and thumb code, making software development and maintenance easier. You can compile them together. And also it's easier to get the best efficiency and performance, in turn making it easier to write the software because there is no need to worry about state switching between ARM and thumb and to try to get the best density or performance. So you're not worrying about state switching at all. We can just write whatever instructions, whether it is 16-bit or 32-bit, together in the same code, and they can be compiled together. So it also has a number of powerful and interesting instructions, which we'll be going to see in the second module, of course. Some examples are like this, UFBX, BF5, BFC. They're like bit field extract. You can extract certain bits. You can insert certain bits in between the register. You can clear certain bits. Then divide instructions, unsigned and signed divide instructions. Then wait for event, wait for interrupt, send event, these instructions. They allow the processor to enter sleep mode and to handle task synchronization on multiprocessor systems. Then instructions to access special registers, MSR and MRS, move to special register from general purpose register, and move special register to general purpose registers to access the special registers. So these are all some instructions which are special in Cortex processors. Another thing that you have in the architecture is the debugging support. Right? We have seen this in the architecture block diagram. The Cortex M3 includes a number of debugging features, such as program execution controls, including halting and stepping, like step-by-step execution, like tracing, instruction breakpoints. Right? In between the program, you can include some breakpoints where at that particular point, we will stop the execution and see what is the result. Then data watch points to particular variables, you can add watch points and see the values of those variable at a particular point, right? Then registers and memory accesses, profiling and traces. The debugging hardware of Cortex M3 is based on a particular type of architecture that's called core site architecture. That's the name given by ARM. So unlike traditional ARM processors, the CPU core itself does not have JTAG interface. Instead, a debug interface module is decoupled from the core, and a bus interface called DAP is provided at the core level. That is debug access port. It is provided at the core level, and through this DAP, that is debug access port, the external debuggers, they can access the control registers to debug hardware as well as the system memory whenever even when the processor is running, right? So the control of this DAP, debug access port bus interface, is carried out by DP device, that is debug port device. The DPs currently available are the serial wire JTAG debug port, that is SWJ DP, that is serial wire JTAG debug port, or serial wire DP, right? Serial wire debug port, that is serial wire JTAG debug port. It supports the traditional JTAG protocol as well as serial wire protocol, whereas serial wire debug port, it supports the serial wire protocol only. A JTAG DP module from the ARM CoreSite product family, it can also be used. Okay, JTAG DP, that is JTAG debug port from ARM CoreSite product family, can also be used for debugging. The chip manufacturers can choose actually from these, which one of these DP modules to provide the debug interface. They can also include an embedded trace macro cell, ETM, to allow the instruction trace. One unit called ETM, that is embedded trace macro cell. The trace information is output via an interface unit called TPIU, that is trace port interface unit. And the debug host, normally that debug host means the PC where you're debugging, right? That is a personal computer. It can collect the executed instruction information through some hardware, that is external trace capturing hardware. So within the Cortex M3 processor, a number of events can be used to trigger debug actions. Debug events can be breakpoints, watch points, or fault conditions, or external debugging request input signals. These all debug events, they can be used to trigger that debug action. Whenever a debug event takes place, the Cortex M3 processor, it can either enter halt mode or execute the debug monitor exception handler, right, and debug. The data watch point function is provided by data watch point and trace unit, DWT. That's called data watch point and trace unit. That is in the Cortex M3 processor. This can be used to stop the processor or to generate data trace information, right? Stop the processor or trigger the debug monitor exception routine, and or to generate data trace information. Whenever the data trace is used, the traced data can be output via the TPIU, right? That is the trace port interface unit. In addition to this, the Cortex M3 processor also provides another unit called flash, patch, and breakpoint unit that can provide a simple breakpoint function. Means in between the instructions, it can insert a breakpoint or remap an instruction access from flash to a different location in SRAM. Right? From flash, it can remap it to another location in the memory. Another unit called instrumentation trace macro cell, ITM. Right? It provides a new way for developers to output data to a debugger by writing data to register memory in the ITM. A debugger can collect the data via a trace interface and display or process them, right? By writing data to register memory in this particular unit, that is instrumentation trace macro cell, The debugger unit, it can collect the data via a trace interface and display that particular data. Right? By doing that, you can find whether the instructions are running properly, whether you're getting expected result from those particular instructions. Right? This method is easy to use and faster than the JTAG output. So all these debugging components, they are controlled by this through this DAP interface, that is debug access port interface bus on the Cortex M3, or by running a program on the processor core, and all the trace information is accessible from this trace port interface unit, that is TPI. Right? So this is about the debugging support, which is there in the Cortex M3 architecture. So apart from this, there is some more things that we are going to see, that is how the stack is implemented and what happens when you reset the microcontroller. So we will take up that in the next class.